Okay, we are finishing our meetings these days. We have the chapter, which is chapter 11, equilibrium, and we have one more chapter. Today, we will see 3 sections from this chapter, and that's all what we need. We will not discuss elasticity. In the next meeting, we will have also another new chapter, but with selected topics. And by this, we will end our material this week. I'm talking about our plan to the end of the semester. In the vacation week, I'll try to prepare a good review for the material. And if I have a time, I will record it. Then in the final week, our meetings will be online, as you know. But I will discuss everything and I will explain everything in this room via Zoom. You can meet me like the online people, they will not feel the difference. It will be ordinary lectures and the lecture will be recorded as usual. That's it. And you can ask anytime. Also, the final week will be just solving examples. We have 2 lectures. These 2 lectures will be, I will try to solve many examples as much as I can to review all the chapters covered in the final exam. Any question about that? Online? I will put a homework on chapter 10. Also, this chapter will have its own homework, and I'll see later, and I'll tell you how many lower scores I will drop from the homeworks and quizzes, and I will put a quiz. Okay. What else I have? I think that's all. Okay, today we'll talk about equilibrium. Previously, we studied the equilibrium for linear motion. Now we'll talk about equilibrium for linear and rotational motion. Then we will talk about, we need to know the conditions of this equilibrium. It is simple. Also, we'll talk about the center of gravity. And there is a simple difference. It's the same as the center of mass, but we will see what is the center of gravity. Also, we will start solving problems on equilibrium and this chapter. We have just 3 sections. It will be a short chapter, this one. Okay. Now, for equilibrium, we know from before that if we have an object with mass m, and this object has many forces on it. The first force is its weight, which is mg. It is downward, right? Our surface is horizontal. We don't have any components. Our xy plane is this one. As you see, it is simple. We have another force that keeps the body do not go inside this table or this surface, which is the normal force. If we have more than, now these are the y direction or the vertical forces. If we have now horizontal forces, we have, for example, 5 newtons, and we have pushing force, which is equal to 2 newtons. If we need our object to be in balance or under equilibrium state, what is the force that we needed? We have 5 to the right, 2 to the left. We need more 3 newtons to the left. Then we can pull it here by 3 newtons. In this case, our object is under equilibrium linearly. If one of you tell me, okay, if I push it by 10 newtons, how can we make it equilibrium? Simply by putting another force tip like this. Or we can put more forces in this direction and this direction, and their superposition give me 10 in this angle. It is simple, we know that. Also, it is simple in rotational motion. Rotational motion, if we have this game, you know it, seesaw, I think, and we have 3 persons. The first one, his weight is downward. Weight 1. Another person, his weight in this direction also. Yes. We have also another person here at the third point, and his weight to this direction, as we know. So we have weight for the first person, weight for the second person, and we have the weight for the third person. Be careful that capital W is the work. Small w is the weight, right? And omega is the angular velocity. This is omega. Okay, now if the first person at a distance from the center of rotation, which is the point O, we need to know this point. Okay, in linear motion, we don't have any reference point. If our x, y, 0 point, which is if it is here, or if our origin is here, or if our position origin is here, we don't have any difference in this problem. But here, we need to know where is our origin, because there's a rotation about that origin. If we put this O, then we have a different problem, but the same physics. Also now, if I gave you, we need to know R for each object. This is R1, this is R2, and this is R3. All of them are vectors. Now, we need to know the forces in our system. Here we have forces, here we have torques. We need to know the torques in our system. Okay, we have the first torque is equal to R1 cross F1. Okay, which is R1 cross the weight for the first object. It is in the negative y direction. We know that. We can find the angle. We will see that by the example. Also, we have tau 2 is equal to R2 multiplied by F2. And again, F2 is the weight for the second person, which is a vector quantity. Now, we have tau 3 again. It is equal to R3 multiplied by cross product with F3. We need now, when we found the equilibrium state here, we computed the vertical forces and the horizontal forces. Now we have 2 directions. These 2 forces are rotating the system counterclockwise, right? And this force rotating our system, this is clockwise, this is counterclockwise. And we know from before, counterclockwise means positive direction, and negative clockwise is negative direction. If I ask you to measure this theta, it is positive because the motion is counterclockwise. But if I ask you to measure this phi, it will be negative because the motion is clockwise. Right? Now, for equilibrium, we need the total torques equal to 0. And there, we need the total forces as vector equal to 0. Okay, and also here we need to find this condition. What are the total torque here? Okay, the total torque is equal to the torques clockwise, which are negative, plus the torques counterclockwise, which are positive. It is simple. We need to this plus this plus this. I'll put them like that for this case. What are the torques? The positive torques. Where are the positive torques? Is it tau 1, tau 2, tau 3? Which one is them? Which one is the positive? The third one. So it is tau 3. This is tau 3. It is positive. And we have tau 1 and tau 2 are negative. So we have negative tau 1 plus negative tau 2. We have negative 2 forces or 2 torques and positive 1. So now we have two conditions. This is the first one, and this is the second one. To reach the equilibrium for our system. We know this condition from before. Now we have this one. Okay? And remember, Newton's first law. Newton's first law talk about zero acceleration. If the object is stationary or moving with uniform velocity, then there is no forces on it. Remember that? So this is Newton's first law. This is Newton's first law in rotational motion. We are repeating our study just like that and put the rotational motion in our mind. Okay? Any question about that? Online? Any question about that? Okay. Again, we are going to finish the material this week, and we will start solving examples and problems as a review in the final week. Okay, next. Center of gravity. Yes. Center of gravity. If you remember from before, and I think if we have a circle, then it's a geometrical uniform shape. Its center of mass, I'm talking about center of mass, it is at its center. If we have a rectangle, it is at its center for a uniform shape. We know that from before. And we computed and found the center of mass for two objects. It is at the line between them. And we can do it for three objects. I think we did that. Now we'll talk about another thing. We need to talk about the center of mass or the center of gravity using the rotational motion. If we have our system, XY plane, and our origin is very important to us, the rotational motion. And we have an object, a point mass. This is mass, which is a point. This is important to be remembered. Point mass. Point mass means it is small compared to our system. For example, this chalk compared to our hole is a point mass, but the table this disk is not a point mass. Okay? The Earth is not a point mass. But if we compare it with the solar system or the galaxy, it is less than a point mass, right? Now, this is a point mass and its position R, it is a position vector, we know that. This is R. And this is the mass. This mass is under the gravity effect. We have G. G is a vector. It is acceleration. And you know that the acceleration is a vector and its direction to the center of the Earth, right? Now we have its weight to this direction as a vector, which is equal to M1G. I name it M1 because we have more than one mass now. And G is a vector, it is downward. Okay. This is M1. If we need to compute the torque, yes, the torque about the origin. Okay, the torque from the first mass, this mass, we have just one mass, is equal to R1, which is this, cross product with the force, F1. But this force is the weight. So we have R1 cross product with the weight, which is the first mass weight. Okay, the weight, it is R1 cross mg. G is the vector. And the cross product will be applied on just G. M is a constant. We can take it outside. This is M1. So the torque for the first object point mass is M1 R1 cross product with G. We have mg is the force, R is the R, this is the torque. Is this idea simple to be understood? What about the theta? I didn't put theta now. But theta, this is the R direction. We start R cross F or R cross W or R cross G. So R at the beginning. We put our right hand to use the right hand rule at R, then we rotate it to reach the force and the thumb direction, which is R going out from the board. This is the direction of tau. It is going out in Z direction. So this will be it. Wait, if this is X and this is Y downward, so this direction is Z. If this is X and this is Z, or sorry, this is X and this is Z, then this is Y. But you understand the physical problem, okay? This is for one mass. What if we have two masses? Remember this, we have M1, R1. M1 comes from the force, and G is alone. Now, what about if we have now another system? We have the first mass, and we have another mass, M2. And we have first R position vector and R2 for the mass number 2. Both of them are or have their weight. This is weight 1 as a vector, and this is weight 2 as a vector, right? I think yes. Okay. What if we need to compute the total torque about the origin? So the total work torque, not work, if I say work, it is equal to R1 But it is equal to, I will put it step by step, it is tau 1 as a vector plus tau 2, right? Which is equal to R1 cross F1 as a force. The force, the first force, it is a weight. We are talking about weight, okay? This is weight 1 plus R2 cross weight, the second weight, okay? What about now each weight? We are manipulating with the weight, with weights, okay? The weight 1 is M1 G. G is a vector. We can't put, if we need to put G1, okay, plus R2 cross M2 G2. But G is the same. Inside this room, G is the same, okay? If this is mass, the first mass, and this is the second mass. We have the same G for them. But if we have, this is the first mass, and the second mass on the top of a mountain, G will be different then. G is different, okay? And this is the difference between the center of gravity and the center of mass. If G is the same for all the objects, then the center of the mass is equal to the center of the gravity. If we have a distant or an extended object or a vast distance between the two objects and G is different between them, then the center of mass, assume this is the center of mass and this is the center of gravity, they will be different than each other. When the other object, that one, the far one, go far and far, then there will be more there is more displacement between the center of mass and the center of gravity because the difference in G. Now we have the same G. G is equal. Again, I will take M outside. It is M1 R1 as a vector cross G plus M2 R2 cross G as a vector. This is for two objects. Now, I need to put a third object. You will see I will put objects to reach infinity. I'm talking about point masses now, right? And I will use a different color to change the background. Okay. For three objects, if we have M1, M2, and M3, it's okay. And then this is R2, this is R1 as a vector, and this is R3 as a vector. Any question online? Here in the class. We need to compute the torque about the origin again and again. So the total torque, it is equal to tau 1 plus tau 2 plus tau 3 as vector. It is equal to, do I need to put this and this to reach this? It is the same. It will be equal to R1 cross M1. We have the weight. This is weight 2. This is weight 3. And this is the first weight. So we are talking about weight just because we are talking about center of gravity. M1, G1, no, G, it's the same. Plus R2 cross product with M2 G plus R3 cross product with M3 G. G is the vector. It is the same thing. So I can now again and again take M outside of this product and put it or engage it with R. So tau total is equal to M1 R1 cross G plus M2 R2 cross G plus M3 R3 cross G. In all of these cases, G is the same. I can take G outside from the both terms or from the three terms like this. It is M1 R1 plus M2 R2 plus M3 R3. It is close the same G, right? I just take G out of these terms. Okay. This is tau total. I told you from before, we are physicists. We can manipulate, we can play with the equations. We can multiply by 1. Okay? We can multiply by x over x or 2 over 2. It is 1. We need to multiply now by this quantity. It is simple. You will know, you will see it. It is the summation of mi over the summation over mi. It will be simple. The summation of mi, it is the total mass. It is m1 plus m2 plus m3 for our system. And we call these masses capital M. If you remember, when we compute the center of mass, these are the total mass in our system. It is capital M. So I will multiply by capital M over capital M, which are the total mass in the system. I will take this one to put it here. Here. And I will put this with G. This M, I will put it with G. And look at this. We have 3-point masses. We have all these masses. This is capital M, which is M1 plus M2 plus M3. But I put them all, package them all together. And assume that my system is just one mass, like this one. If you assume this is M1 and this is M2 and this is M3, if we combine them together, we have M1 plus M2 plus M3, they are M capital. Now, G multiplied by M. What is G multiplied by M? We know that. Mg. What is the weight in general? This is the weight, small letter. This is the weight for my system. It is a vector. It is a cross product by, what is this? If you remember from before, we have x center of mass is equal to M1 x1 plus M2 x. Is it clear? I will put it in a bigger font. Now we will deal with the center of mass. X center of mass is equal to M1. Remember that. X1 plus M2 X2 plus and so on, M3 plus X3 and so on, over M1 plus M2 plus M3 plus, which is capital M. This is capital M, which is that one. What about Y? Center of mass. It is equal to M1 Y1 plus M2 Y2 plus M3 and so on, Y3 and over the capital mass, which is the total mass. What about R of center of mass? It is simple. Maybe R capital, maybe R small. Okay. It is x center of mass in I direction plus y center of mass in j direction. It is a position vector. If we have z direction, z center of mass in k direction, it's okay if you like. But in our case, we have just xy. Okay, now this quantity, we don't see here x or y in our system, but we see now R1, R2, R3. It is x and y together inside the position vector for the center of mass. So this quantity is R capital or R small, as you like, for the center of mass. Did you remember these equations? Maybe yes, maybe no. But I think they are simple in general. I will solve examples. I need you now not to focus in the equations. I need you to focus in the physics in the problem. Okay? Now we have the total torque, which is T tau 1, tau 2, tau 3, will be equal to R for the center of mass cross with the wave for the system or for the center of mass. I'll draw it here. If we have mass 1, mass 2, mass 3, and this is the center of mass for them. The total torque for the first one, and the second, and the third, if you add them together, assume that these points are not exist, and we have just one main mass with one position. The total effect for these points is just as the effect of one point, which is the center of mass of these objects. If I told you to compute the torque for your body parts, you are going to compute for the right hand and the left hand and the leg and the rack and the head and all of that. But another one will find where is the center of mass for his body and compute it once for all the body, right? And that's what we do, what we are doing here. Now, in physics, we can assume our system contains point masses, and the number of these point masses goes to m, goes to infinity. It's okay. I can put infinite number of point masses inside this room. Okay, and I can compute the total torque for them. Maybe one point is here, and the other one is there, and that one, that place has a point, and so on. But if I compress them and localize them in a region, assume that these points are a dust, and this dust is collected together, and it will form a planet or a star in the universe. Okay, and because this dust was rotating, it has an angular momentum, and when it combined, then just the same experiment like this person who are rotating, and when he collect his path, his omega was greater. The dust is rotating. When it comes to be a planet or a sun, it will be faster. Now, if my masses are compressed together and they are localized, this object will be a continuum mass or an extended mass. It is just like this mass or this mass or this mass. It contains infinite number of points, right? And they are collected in a certain region. So I have now, for example, another continuum mass inside my system. And if I need to compute the angular moment, the angular force or the torque for this mass above the origin, I will not go. By the way, in the graduate studies, we compute the torque for all the points in this mass. It is difficult to us. But here, we need just to know where is the center of mass and compute the torque for this center of mass using our center of mass. I will not compute M1, M2, M3, M infinity. I will just assume this object, extended object, just like a point mass concentrated at the center of mass. In this case, we are not talking about center of mass, we are talking about center of gravity. Because G here is the same as G here, because we are in a localized place. But what if this is the air, H, yes, and our object like this, like the science fiction movies, we have, for example, this spaceship. It's like this. I think it was like this. They destroy the air. Okay. Now, G here, we have G1, G2, G3, Gm, or G infinity, depending on the altitude on the Earth's surface. You know that from before. Okay. Now, the center of mass is the center of the geometrical object, but center of gravity is dragged to the more gravity or the more weight. Where is the more weight? We have capital G here. We have a small g here. The weight is the mass. So this mass, assume it M1, for example. And this mass M2, which is half-half, so it will be MM. But G here is bigger. Then the weight here is bigger. Then center of gravity will be dragged to the bigger weight. And you, inside this space shuttle, you will be more weight downward than upward. Okay? In black hole problem, the weight inside the Schwarzschild region or horizon, your weight here, not like this, the difference will be 1 Newton or 2 Newton. Your weight here will be infinity, for example, and your weight here is, for example, 600 Newtons. So your downside weight will reach infinity when you are putting inside the horizon effect or horizon S. Horizon, Schwarzschild horizon. Yes. Now we are talking about continuum object, and because of G is the same everywhere, then center of mass is center of gravity. Is that understood? Online, offline? Okay, now our problem is come back to this simple case. Tau is equal to R multiplied by the weight for just one mass as cross product. Okay, we have just 1 point mass now, and we need to know where is this point, where is this R. We need to know the R. That depends on the object. We know how to find the center of mass, assuming G is the same or constant. We know that for uniform objects, the center of mass is at the center of that object. Now, I'll use this uniform object. It is a rectangle, right? And we know that its center of mass at, it will not appear, I need another color. Okay, we know that center of mass is at the center of the geometry of that object. We have this. So, and this. So our center of mass is here. Are you agree with me? What if we use experiment to doing this? Not our knowledge in math. Okay, in physics, you will see that online. I will share the screen now, and I will talk. Sharing, where sharing? Share screen. Share. No, not this slide. Second slide. But before, I'll do this. And I'll okay. Turn off the lights. Not, okay, you can see the monitor now. Now we have many cases. Can you see that online? You can see the shared monitor. I will zoom it. Okay. We have the uniform shapes, just like the disk or a sphere or a triangle or a cone, and so on. It is simple to find the center of mass. We have semi-uniform objects, just like this one. We can divide it to a uniform shapes. For example, I divide it to a triangle. This is the way how to find the triangle. I need to take the half of the angles of the heads, and I can find the center of mass for this triangle. I can find the center of mass for this triangle. No, not triangle. Yes, triangle. And I can find the center of mass for this rectangle. Also for this one. The center of mass for the two shades on the line between them. I can find it. Now I have 3 points. 3-point masses. The first one, the second one, the third one. That's okay now. I can find the center of mass for all of them. For example, I can use the calculations and I can find that the center of mass for the first 2 points on the line between them, or the first and the third point on the line between them, or in the third and the second point on the line between them. And pick any points. For example, this one for these first 2 points, and I have this one also. The center of mass will lie on the line between the 2 points, the third mass and the first center of mass. And if I compute it in any way, I will find the same center of mass in all the ways. Okay. Now another thing. Online, can you see it well? I hope yes. I'm talking about uniform objects. Now, what if we have these objects for non-uniform shapes? I will do an experiment now to do this one. We just take that non-uniform shape and we can hang it from different points, and the intersection between the lines, the vertical lines, we can draw a line. That intersection between these lines will give us the center of mass. It works, this method works for the uniform shapes because it works for everything, for all the shapes. This shape is a plan, but what if we have a body like this one, which is a volume? We need to hang it from more than 3 points, maybe 4, and take many lines inside it. The intersection of these lines at just one point. If we can't see that point, it will be the center of mass. For example, for the human, our center of mass at this point when we are standing up. But if we change our shape, the center of mass will change us. For cars and vehicles, for this bus, London bus, if it passes a road with an angle, as we see, if this angle is bigger or larger than a critical angle, it will fall down. Because of that, for this vehicle, and for example, the instruction vehicles, for like the forklifter, this one, which lift the things, it should have a big mass, and its center of mass should be close to the air, to the ground. Because in any case, we have a slope, we keep the center of mass above the wheels. Do not go out of it. For example, also, the race cars, these are not the race cars, but the race cars also need to have a center of mass below, not high. Some of cars, for example, I will not talk about names. Some of cars, four-wheel cars, its center of mass is high, like this one, and it is dangerous to ride it, to drive it in fast way on the curves, because the center of mass will be out of the place of where wheels. But other cars, it is stable to the ground. Okay. For animals, for us also, we are walking by moving our legs and foot. Now, if we keep ourselves like this, we will fall down. And you know that famous dance for Michael Jackson, Allah. He do this. You can't see it on YouTube. He just doing this movement, right? And he is not performing. And then I see what is the reason for that. Their shoes. I'm sorry for that. Their shoes have a place here to pin a nail on the ground, and they fix their shoes and make this movement. Do you understand me? Now, for animals, for T-Rex, for example, these animals have just 2 legs. It is difficult for them to keep balance. Not just like horses or deer. They have four, but these have two legs. For example, the dinosaur, this T-Rex, because of its large tail, it keeps itself balanced. For the chicken, for example, it has small food, but how much is that now? But it keeps its balance and equilibrium state by moving its hip like this when it's walking. You can watch that, okay? And you can watch these things in all animals. And these animals, let's study physics, just by nature, right? Yes, we have it. Okay, I'll stop sharing now. Yes, to back. Great, thank you. I will move back to this. Yes. Right. Now I'll start solve. I think example. Any question so far? Offline, online? I'll do the experiment. Now, if we try this by hanging, we need to draw a vertical. Now I'm hanging it freely. We need to draw a vertical line like this. And that we need to choose another point and hang the object from it. We need to draw another line. Then we'll see that the same center of mass by using this experiment. But what if this shape is not uniform? I will change it. Is it the same uniform shape? The answer is no. Now I will use the same experiment. I will use the clear side. Okay. I'll use this here. This. Now I need to draw my vertical line. Another vertical line. This is the old one. So now our center of mass is dragged toward the bigger mass or the bigger material or quantity. We have less mass in this place now. If you remember, this is our mass from before. This center of mass will come back to the center of the rectangle. But when we remove this, the people here, the mass here, pull the center of mass to their direction. And we have a new center of mass. Is that understood? Online? I told you I felt like a hero when I answered this question. How can we find the center of mass for the non-uniform shape? It was the first question that I answered in my study in the university. Nobody knows it but me. Okay, now we will start now 11.3, which is application and problems on balance. and it is the last section in our lecture today. If we have this system, this is the first example. We have this system. We have the first mass. Is it the first? No, this is the third. We have our origin is here. This is O. The rotation is about this point. We have a mass here. This mass is the second mass, and we have a mass here, which is the third mass. The givens M1 is equal to M2 is equal to M3 is equal to. No, M is the way they give us the weight directly. Weight 1 is equal to 3 newtons, and the direction is downward. You know that. And weight 2 is equal to 8 newtons, and the third weight is equal, I think, to 10. Yes. Okay, what about the radius for each mass? R1 is equal, R2 is equal to, R3 is equal to, R1 is 4 meters to the positive x direction. This is R1. This is R2 to the positive x direction. Okay. R2 is 1 meter. This is positive I direction. This is positive I direction. R3 is 2 meters. In negative I direction. We know that. This is R3. I'm asking now, is this system goes under equilibrium state, situation or state? Is it balanced or not? Is there any total torque? Is the total torque equal to 0 or not? All of these questions are the same. Now we have 3 objects, and this is the origin, or this is the point of rotation. We have, this is the first weight, this is the second weight, or the second force, and this is the third one. Okay. Again, I'll put that. This is F1, which is the weight, the first weight. This is F2 or W2, and this is F3, which is the weight number 3, and this is the origin. Do we have balance? We'll see that. We have 3 forces, so we have 3 torques. We need to compute these torques. The first torque as a vector is equal to R1 cross product with omega 1, which is the first force. It is equal to R1 is 4 multiplied by omega. What? Not omega, W1, I'm sorry. 3 newtons multiplied by this thing. We know it. It is sine theta. We know that the cross product is RW sine. What is theta in our case? Who can tell me? Online, offline, anybody? Aywa? صح. Right. Because this is R. And we need to go from R to F. We need to go this way. It is 270 or 3 pi over 2. This is 270. Sine of 270 is negative 1. So this will be equal to, I'll put there. We don't need this now. Which is equal to negative 12 Newton meter. It is not energy, okay? Negative means that the rotation is clockwise. Right? Now, tau 2. As a vector, we find the direction, so it is a vector. It is equal to R2 cross product with W2. It will be equal to R2. How much R2? It is 1. Multiplied by the mass or the weight, which is 8, sine the same angle, because this is R and this is the force. This is R again, R2, and this is the force, 270. It will be also negative 8 newtons meters. It is not energy again. And the direction is clockwise, which is negative. What about tau 3? I will not put it there. Tau 3 is equal to R3 cross W3. It is equal to R3 is how much? It is 2. I'm not taking it negative 2. R from the position. It is not positive, negative x axis. Okay? It is R from the position. Okay. What about the direction? I am putting the direction inside the sign. Okay, we have negative or positive. How much the weight now? It is 10. Sine, how much theta now? This is R3, and this is the force. It is 90, which is 1. So this will be equal to positive 20 newtons meters. Positive means counterclockwise. Now, without doing anything, I'm asking, do we have balance? Do we have equilibrium? How much the total torque? Now, it is positive 20, negative 20. It is 0. Yes, we have equilibrium. Any question about that online? Any question about anything in the first part of the lecture? Now I will talk about the second example. It is important example to know how much our body is strong. Assume this is our arm. We are moving this arm from this point, not from there. Don't imagine that your force in your body is affected here. Your force is affected at this point. Your muscle is connected to the bones at this point here. It is a small distance. Small distance. So you are moving your arm. This is the fixed point, which is at the knee. No, elbow. Yes, I have very pain there. And your force is there from your muscle acting just here. If you can lift using your arm 20 kilograms, your muscle here apply more than that many times. I will ask you now to do this experiment. Give me any heavy thing, anything like this one. You can see that line. Okay. It's not that heavy, but if I need to lift it, look, this is my fixed point, and I need to lift this from here. From here. It's simple. It's easy. This is the point of the effect of the force. What if I need to lift it from here? It will be difficult. It is difficult from here. Okay, but it is simple from here. Now, your muscle do the same thing. You will see that it is a short example, but has more concept in it. If we have this system, this is another example. This is O, and this is your R, and your force is applied here. This is F, B, your F, or applied force. And we have a mass, which is the physics book, which is, it is more than 4 kilograms, by the way. We have the mass, and this is the weight, which is the mass multiplied 4 multiplied by G, which is 9.8. Okay, now we have the distance of the mass. I will name it also you have the mass of your arm. We assume that the center of mass of your arm at this point, and the mass has its weight. I name this one is 1, 2, 3. This is 3. This is weight number 2, which is equal to 2. This is weight number 2 equal to 2.5 kilograms multiplied by 9.8. This is the point 1, the point 2, and this is point 1. This is 1. And this is a 3. To have a balance in our arm, how much the muscle force, which is FB or F1, I need to know R1 equal to, R2 equal to, and R1 equal to, R2 equal to, R3 equal to. How much? Let me see. R1 is 0.04 meters. It is just 4 centimeters. Less than 2 inches. The place where your muscle affect. R2 is 16 centimeters, which is 0.16 meters, and the third one is 38 meters. Yes, okay. We need to find F to have a balance system. Okay. To have balanced system, we need to find total torque equal to 0, which is equal to torque 1 plus torque number 2 plus torque number 3 as vectors. Right? Okay, the first torque, this one, is equal to the applied force, which is R1, which is, I will apply the numerical values directly. Multiplied by the force, FB, what we need to find. This is R, and this is the force. The angle is 90. Sine 90 is 1. We are done. I multiplied by 1, which is the sine. Okay. Tau 2 is equal to the radius, which is 0.16, multiplied by the weight, which is 2.5, multiplied by G, which is 9.8. The angle, we compute it now, it is 270. It is multiplied by -1. Right? the final torque, it is equal to the R, to the radius, which is 0.38 meters, multiplied by the weight, which is 4 multiplied by G, multiplied by -1 again. We have the three terms, we need them to be equal to 0. Add them together. Okay. If you add them together, you will find that 0 is equal to negative 14.9 plus negative 3.9 plus 0.04 multiplied by FP. We need to find FP. First, we need to reorder our equation. The negative sign will be positive when we move it to this side. Then we need to divide over this number. It will be equal to 18.8 over 0.04. 18.8 is this plus this with positive sign because we move them there. This will be equal to 470 newtons. 470 newtons. It is almost 47 kilograms. To lift the book, which is 4, and your arm, which is 2 and 2.6. So the mass here is 6.5. Your muscle apply a force to lift it to lift 47 kilograms. I remove G. G is almost 10. Do you imagine that when you need to lift 6.5 kilograms, which is a book and your arm is 2.5. You will apply a force to lift at this point to lift 47 kilograms. Now, if I have a heavy mass or I need to lift a person, and you did that many times, I think. When you tell him to when you need to hang him, you hang him at this point. You are strong here, but you are not strong here. Okay, God created us to, and the engineer creates the machines also to do this. That's right. We apply a huge force to lift a huge mass at this point. But imagine your hand, your arm, it's just like this strength. You will not, if you need to move this thing, like T-Rex, his arms are small. He can't use things. It is strong, but it is small. You will not be able to move this from here to here. You need to make it more than one step, right? But God make you have long arm. We don't need that force. We will not lift big things. We are just lift ourselves and that stuff that we are using it. It is small things. When you take the ratio between this and this, it will be more than 7 times. More than 7 times. Do you imagine that applying? So our bodies has more force than what we thought. Okay, that's it. We are done now for today. We finished this chapter 11 by one lecture. We have studied just the 3 sections. I'll try to select the most important topics in chapter 14, I think. I'll look at the syllabus. And we will finish the material this week again. And we will start the review, starting from the starting date of the vacation. We don't have vacation in general. We are academic. We are students. Any question online of so far? Thank you so much. I will.